Matrices and vectors, what are they all about? So in this introductory lecture, I want to introduce some vocabulary that will set the tone for the rest of the course. So let's jump right into it. So the first thing to start with is basic notation. When mathematicians use this symbol, sort of fancy R, what they're referring to is the collection of all real numbers. And this is something that you're likely familiar with. These are all of the numbers that are on the so-called real line. So most of the numbers that we know and love, like the number 0, the number 1, the number 2, the number -1, the number -2, and even more complicated numbers like maybe the number 1/2 or even pi are all real numbers because they fit on the real number line. And another piece of notation that mathematicians use is this fancy E symbol. And this fancy E symbol is used to indicate membership. So how do we use this symbol properly? Well, we saw up here that the number 0 is a real number. So what the language we used, or the writing that we use to efficiently communicate this, is we write 0 fancy E R to efficiently say that 0 is a real number. Same here goes for the number 1, the number -2, and the number 1/2. But sometimes we work with things that aren't real numbers. So for example, the word hello is a word in the English language. It's not a real number. So we can efficiently communicate this by writing hello and then fancy E striked out R, or we cross out the fancy E to indicate that the word hello is not a real number. And when we use the term number in this course, we likely won't use the term number. We might use the term scalar. So this is very common. Okay, so now let's talk about the first sort of big definition for the course. So this course is called Matrices and Vector Spaces, and in order to understand these concepts, we have to start with the notion of a vector. So a vector in Rn is a list of n scalars organized vertically into a list. So when we talk about vectors in this course, we're talking about objects that look something like this. So here, let's look at our first example. Here we're using the bold notation to talk about vectors. And by definition, a vector in Rn is a list of n scalars organized vertically into a list. This vector v here is a list of 2 scalars organized vertically into a list. And for this course, what we'll do is we'll bracket this vertical list with, I guess these are just called brackets. The second example here is a vector w. And this is a list of 3 scalars, 3, -5, -5, organized into a vertical list and then bracketed off. Here we have another vector. This is bold x. And this is just a list of 4 numbers, and all of the numbers are equal to 1. So this is a perfectly valid list of 4 numbers. And our last vector in our example here is a vector consisting of the numbers or scalars -7/9, 0, pi, and 1. So these are all examples of vectors. Now, again, we use this fancy E notation to indicate membership. So, for example, our first vector here, v, was a list of 2 numbers. And so what we would write is v fancy E, so v belongs to R2 to indicate that there were 2 numbers stored in this vector. Our second example was w, which was a list of 3 scalars. So here it's appropriate to write w fancy E R3. This efficiently communicates that w had 3 numbers stored in it. And then the 2 last examples here, x and b, both stored 4 numbers in them. So we would write x comma b fancy E R4 to efficiently communicate that x and b were vectors in R4, meaning that they stored 4 numbers. Note here, we also use this crossout notation to indicate that something doesn't belong somewhere. So the vector v that we started with stored 2 numbers, not 5 numbers. So it's appropriate to write v and then fancy E crossed out R5 to efficiently communicate that v did not have 5 numbers inside of it, it only had 2. And when we're talking about the numbers inside of a vector, so the numbers or scalars stored in a vector, it's common to refer to those numbers as coordinates. So what we would say here is that the coordinates of v are 1 and -2, and for example, all of the coordinates in x are equal to 1. Okay, so that's the basic terminology for vectors, which is one big part of this course. But perhaps the biggest part of this course is the notion of an m by n matrix. So by definition, an m by n matrix is an array of scalars that has m rows and n columns. So here's our first example of a matrix, and it's a rather big one. Here we have we're using this capital letter notation to refer to matrices. So here we're calling this matrix capital A, and let's look at what the rows and the columns are. So by definition, an m by n matrix is an array of scalars with m rows and n columns. Well, the first row in this matrix is sort of this first list of 1, 2, 3, 4, 5, 6 numbers in the matrix. The second row is this sort of second horizontal list. The third is this third horizontal list, and the fourth is the fourth horizontal list. So here we would say that this matrix has 4 rows. But we also have columns here. So the first column in this matrix is this first vertical list of numbers. The second column is this second vertical list of numbers, and so on and so forth. So all told here, this matrix has 4 rows, so 1, 2, 3, 4, and 6 columns, 1, 2, 3, 4, 5, 6. So the way we would communicate this is we would write A belongs to, so A with the fancy E symbol, R to the 4 by 6. So in this notation, we aren't multiplying 4 and 6 together. We're using this to indicate the shape of the matrix or the dimensions of the rows and the columns. Now, when we're talking about matrices, one thing we'll want to do is sort of look up the various scalars that live inside a matrix. So by definition, the ij entry inside of a matrix is the scalar that lives in the ith row and jth column. So here we're working with a perfectly good matrix called A. And just by glancing at this matrix, we can note that this matrix has 1, 2, 3, 4, 5 rows and 1, 2, 3 columns. So let's say that someone asks us to look up the 4, 2 entry, so the 4, 2 entry of this matrix. One thing that's common to do to refer to this entry is to use this lowercase notation for the variable we use to define the matrix. So here we define the matrix as capital A. So if we're looking for the 4, 2 entry of capital A, we might write this as lowercase a sub 4, 2. And what is this number? Well, according to the definition, we should look up the ith row. So here we're looking for the 4th row, 1, 2, 3, 4. And then we should look at the jth column, which is 2. So we should look at the second column. And then what is the number that lives in the 4th row and second column? Well, apparently this is the number -2. So we went to the 4th row, second column. We found the number -2. So here we would write that A sub 4, 2 equals -2. Okay, so what I want to do now is I want to start to describe some adjectives that describe matrices. So we're going to use language to describe matrices a lot. So I want us to familiarize ourselves with some of the basic language. So our first adjective is the adjective square. So we say that an m by n matrix is square if m equals n. And if you think about what this means for a moment, all this means is that the number of rows in the matrix is the same as the number of columns. So here are just 3 shapes that one might encounter for a matrix. If we look at our first example here, what we're doing is we're referring to a generic shape that a matrix might take. And in this generic shape, the number of rows is 1, 2, 3, and the number of columns is 1, 2, 3. So here we're looking at a 3 by 3 matrix. The number of rows equals the number of columns, so it's appropriate to call this matrix square. If we look at our middle example here, the number of rows is 4, and the number of columns is 4. So again, it's appropriate to call this matrix square. However, if we look at our example on the right here, we can count the number of rows, which looks like it's 4, and we can count the number of columns, which looks like it's 6. So the number of rows is not the same as the number of columns, so this matrix is not square. So this is just one way to taxonomize matrices. Some matrices are square, some matrices aren't square. One thing that turns out to be useful in navigating the entries inside of a matrix is the diagonal, or sometimes this is called the main diagonal of a matrix. So the diagonal of a matrix refers to all of the entries in the matrix whose row number is equal to the column number. So these are all of the I, comma, I entries. So here I have a couple of various shapes for what a matrix might look like. This matrix A is a 3 by 3 matrix, so this one happens to be square. Where is the diagonal? Well, the diagonal refers to all of the entries whose row number matches the column number. So in this case, this would refer to the entries A11, A22, and A33. What about for this matrix B here? This is not a square matrix, but that's okay. We can still talk about the diagonal of this matrix, or the main diagonal of this matrix. So this matrix is 4 by 3. Well, what are the diagonal entries? The diagonal entries, again, are all of the entries whose row index matches the column index. So here we should be looking at the B11, B22, and B33 entries. So no matter how we filled up this middle matrix, whatever these three entries are, that's referred to as the diagonal of this matrix. And for our last example here, we have this matrix C. This one looks like it's a 3 by 4 matrix, so there's 3 rows and 4 columns. Again, the diagonal refers to all of the entries in this matrix whose row index matches its column index. So here, that would be the entries in the 1, 1, 2, 2, and 3, 3 position. So lots of times the diagonal is sort of a reference point for talking about where certain entries are inside of the matrix. So it's useful to have this terminology at our disposal. Okay, so maybe our next adjective can build off this concept. So it turns out that one useful type of matrix in linear algebra is this notion of an upper triangular matrix. So we say that a matrix is upper triangular if every entry below the diagonal is equal to 0. So let's look at a few examples here. So our example on the left is a 3 by 3 matrix. And if we look at the diagonal of this matrix, that's everything in the II position, so the 1, 1, 2, 2, and 3, 3 positions. And if we're interested in whether or not the term upper triangular applies to this matrix, what we should do is we should section off everything on the diagonal and above and verify that everything outside of this section is equal to 0. In this case, everything below the diagonal, as we see, equals 0. So it's appropriate to call this matrix upper triangular. In our second example here, we're dealing with a 4 by 3 matrix. And again, if we section off everything that's on the diagonal and above, if we're curious whether or not the adjective upper triangular applies to this matrix, we should look at everything outside of this section and verify that it's equal to 0. So here, again, everything below the diagonal, so everything outside of this section, is equal to 0. So it is appropriate to call this matrix upper triangular. In our third example here, we're looking at a 3 by 4 matrix. And to verify whether or not this matrix is upper triangular, we should section off everything on and above the diagonal, and then verify that everything outside of this section is equal to 0. And in this case, we actually have a problem because this entry 9 is in the 3, 1 position. So this is below the diagonal, and it's not equal to 0. So we say that this matrix is not upper triangular. So as we move on in the course, we'll find that upper triangular matrices turn out to be useful in certain situations. So this is our first step to understanding what those actually are. And if you wanted maybe a more mathematical way to say that a matrix is upper triangular, one way to say it efficiently is to say that the ij entry must equal 0 if the I index is greater than the j index, or the row index is greater than the column index. So if we look at our example that failed over here, the reason this example is not upper triangular is because of this 9 in the 3, 1 position. Well, 3 is greater than 1, which means, and because that entry is not 0, we say that this matrix is not upper triangular. And just like we have upper triangular matrices, we also have lower triangular matrices, which are similarly useful. A matrix is called lower triangular if every entry above the diagonal is equal to 0. So let's look at some examples here. Here I have 2. In our example on the left, let's say that we wanted to test whether or not this matrix was lower triangular. Well, what we do is we section off everything on the diagonal and below, and then we verify that everything outside of this section is equal to 0. In this case, everything outside of this section is equal to 0, so this matrix is lower triangular. In our example on the right here, let's say we wanted to test whether or not this was lower triangular. Well, again, what we do is we section off everything on the main diagonal and below, and then we verify that everything outside of this section is equal to 0. But here we have a problem because this 5, which is in the 2, 4 position, is above the diagonal. And this 5 is not equal to 0, so we say that this matrix is not lower triangular. And just like with upper triangular matrices, there's a more mathematical way to say that a matrix is lower triangular. Saying that a matrix is lower triangular is equivalent to requiring that everything in the ij position equals 0 if I is less than j. So what this means is that we need all of the entries to equal 0 where those entries have a row index that is less than the column index. Another adjective that turns out to be useful is the notion of a diagonal matrix. So we say that a matrix is diagonal if every non-diagonal entry is 0. So if you think about upper triangular matrices, what we needed was only that everything below the diagonal was 0. If we think about lower triangular matrices, what we required was that everything above the diagonal was 0. Now if we enforce both of those conditions, what we're saying is that we don't care what's on the diagonal, but we want everything else to equal 0. So here we have a few examples. In our leftmost example here is a 3 by 3 matrix. If we just focused on the diagonal, I don't care what's in those positions, but if I'm going to call this matrix diagonal, I need everything not on that main diagonal to equal 0, and that absolutely applies here. So we have 1, 3, and 0 on the diagonal, but 0's everywhere else. So this matrix is diagonal. Here we have a 4 by 3 matrix, and if we're curious whether or not the adjective diagonal applies to this matrix, we look at all of the entries on the main diagonal. So here we have 0, 0, and 2. But I don't care what those entries are. I want to know that everything outside of those entries is equal to 0, and in this case that does apply. So this matrix is appropriate to call diagonal. And then in our third example here, we're looking at a 3 by 4 matrix. If I'm curious whether or not I can use the adjective diagonal to describe this matrix, I look at all of the entries on the diagonal. Again, I don't care what those entries are. I just want to know that everything outside of this section is equal to 0. And here we have a problem because I have a 7 that's in the 1, 3 position. And that 7 is outside of the diagonal and it's not equal to 0. So it is not appropriate to call this third matrix diagonal. It's worth noting that this third matrix is upper triangular because everything below the diagonal is equal to 0, but it's not upper triangular. Or sorry, but it's not lower triangular. And a more mathematical way to say that a matrix is called diagonal is to require that every ij entry is equal to 0 if the row index is not equal to the column index. So we'll find later in the course that diagonal matrices end up playing a very useful role in simplifying certain kinds of problems. We also have 0 vectors and 0 matrices. So it actually turns out to be useful sometimes just to fill up a vector with all zeros or fill up a matrix with all zeros. And the notation that I'll typically use for this is I'll use this bold O notation. So here, bold O sub 2 is referring to the vector with 2 entries, both of which are equal to 0. Here we're looking at O sub 4. This is a vector with 4 entries, all of which are equal to 0. And here we're looking at the 3 by 2 0 matrix. This is bold O sub 3 by 2. So this is the 3 by 2 0 matrix. So this matrix has 3 rows and 2 columns, and all of the entries are 0. And in this rightmost example here, we're writing bold O sub 4 by 4. This is referring to the 4 by 4 matrix where all of the entries are simply equal to 0. And sometimes the context is clear. So meaning that sometimes it's clear that we're having a discussion about vectors with 4 entries or matrices with 3 rows and 4 columns. So sometimes we'll just write O and then we'll omit the subscript because sometimes, well, we're lazy. Another extremely important matrix is the n by n identity matrix. So the n by n identity matrix is the n by n matrix that has ones on the diagonal and zeros everywhere else. So for example, so the notation we use here is I sub n, where n refers to the number of rows and the number of columns, because the identity matrix is a square matrix. So here I sub 2 is the 2 by 2 matrix, where all of the entries on the diagonal are equal to 1, and every other entry is equal to 0. So this matrix happens to have 2 1s on the diagonal, and then 2 zeros in the other 2 positions. I sub 3 refers to the 3 by 3 identity matrix. So this is the 3 by 3 matrix that has 1s on the diagonal and zeros everywhere else. And then I sub 4 refers to the 4 by 4 identity matrix. Here again, we have 4 1s on the diagonal and zeros everywhere else.